Welcome to lecture 37. In this lecture, I will talk about the evolution of the scale factor, mostly for flat universes. So recall that in lecture 35, we found the Friedmann equations for cosmology. Using the shorthand notation H defining the ratio of A dot over A, these equations are seen in equation 37.1, where again A is just the scale factor of the universe. So in this lecture, we want to now consider actual solutions for the scale factor that arise as a consequence of solving the Friedmann equation. So if you look back at equation 37.1, there are three unknowns. There is A, the scale factor A, or H. There is the energy density epsilon and the pressure P. However, we only have two equations. So clearly, we need another equation in order to close the system and solve for all the quantities. This additional equation is usually taken to be the equation of state, or the relation between the pressure and the energy density of the matter that we want to describe. So the equation of state gives certain cases. For instance, the simplest one is the equation of state for dust, where basically we assume that the matter is just in form of small particles which have a fairly high energy density because it includes the rest mass of the particles. But its pressure is much, much less than this. So basically, we can assume the pressure to be essentially zero. For this equation of state where we have dust, the matter part of the equation simplifies tremendously, and we just get an equation that looks like this, 37.3. Of course, we can also consider other equations of state. In particular, we can try to parameterize the possible equations of state for matter by assuming that there's a linear relationship between the pressure and the energy density with this linearization parameter be constant. So obviously this includes the case of dust where W here is just zero, but it also would include the case of pure radiation. So if you want a pure electromagnetic radiation field, where W is 1/3, so that the energy density is 3 times the pressure for pure radiation. Note that we can also describe pure vacuum energy, a pure cosmological constant, because so recall that these pressure and energy density include the contribution from the cosmological constant or the vacuum. We can do that in particular by setting W equal to -1, where basically the energy density is exactly equal to minus the pressure. And that's precisely the relation that we get if we turn off all other forms of matter and just have a cosmological constant, if you recall how we sort of defined these quantities 2 lectures back. However, in general, of course, the equation of state is not linear. So for real matter, you will typically not find a constant parameter W that gives you the equation of state. It is an approximation. However, it is very useful to come up with analytic solutions of cosmology that nevertheless captures some of the relevant properties of the matter. Okay, so if we now stick with this approximate equation of state, we can plug it into the matter part of the Friedmann equations, and we get, again, an equation that's linear in the energy density, which we can solve. So specifically, because it's a linear ordinary differential equation, we can find a solution. It is straightforward to find this. So we get that energy density as a function of time is a constant times essentially some power of the integrated Hubble constant. And this basically means that we get a solution that involves the ratio of the scale factor times 0 and time t to some power, where the power depends on the equation of state. Now, in order to simplify the writing, we can use notation that denotes all quantities that are evaluated at time 0 by a naught. So epsilon of t0 is equal to a epsilon naught, and a of t0 is equal to a naught, so that the equation takes a slightly simpler form. So now that we have this solution for the matter part of the Friedmann equations, we can plug it back into the second Friedmann equation, the geometry part. And this second equation then reads like equation 37.7. We can divide this equation by h squared, and we find a different form of the same equation here, where I have rewritten the solution for the energy density in terms of the energy density itself. Now let's define a critical energy density EC as 3 times half squared over 8 pi g. The reason being that since we have a 1 here on the left-hand side and we have an energy density there, whatever is in the denominator here also has to have units of energy density. So we can define this to be the critical energy density. The reason for calling it critical energy density will become clear in a second. So by doing this, then in terms of this EC here, we have this equation here, where I just want to point out that despite the writing here, the critical energy density is not a constant because it depends on the Hubble function h of t. It looks like cosmologists like defining parameters. So we will define another parameter, which we call omega, which is now called the density parameter. And we define this as the ratio of the energy density and the critical energy density. So in terms of this quantity here, then the second Friedmann equation that we have to solve is kappa over a squared h squared equals omega minus 1. Since we have a square here in the denominator, it must be that the sign of the left-hand side is exactly equal to the sign on the right-hand side of this equation. So if kappa is positive, the right-hand side has to be positive. If kappa is negative, the right-hand side has to be negative. If kappa is 0, then the right-hand side has to be 0. In particular, if we consider the case of a Euclidean geometry where kappa is exactly 0, we have a flat universe, and as a consequence of this, we must have that omega is exactly equal to 1. In this case, then, the energy density must be exactly equal to the critical energy density, which is why it was called the critical energy density in the first place. So the critical energy density is the energy density where the density parameter is exactly equal to 1, and as a consequence, the universe is exactly flat, because then kappa has to be exactly equal to 0. Let's now go ahead and try to get a solution for the scale factor for this critical energy density case. So the Friedmann equation for kappa is 0 then looks like this, where I have plugged in again the value for our solution for the energy density. So you see the equation of state parameter W appearing here. And since the Hubble parameter here is a dot over a, we have one equation, one differential equation in terms of the scale factor a. So we can solve this equation now to get a solution for the scale factor. A straightforward answer to solve this equation is to use a power law. So we will use the ansatz where the scale factor is parameterized as a constant times the ratio of t over t naught to an arbitrary power alpha, where alpha is taken to be constant. So in terms of this ansatz, then h, which is a dot over a, becomes simple. It's just alpha over t. And we can plug this back into the Friedmann equation such that the Friedmann equation takes the following form. On the left-hand side, we have t over t naught to some power that involves alpha and the equation of state. And on the right-hand side, where we have the h squared, we just have alpha squared over t squared. Now, the point is that there are constants on both sides, which presumably have to match, but the solution really sort of is only a solution if the power of t on the left-hand and the right-hand side of this equation is the same. So this means that here we have t to the minus 3 alpha 1 plus omega alpha. Sorry, t to the minus 3 1 plus omega 1 plus w alpha is on the right-hand side, and on the right-hand side we have t squared. So in order to have this 2 match 3 alpha 1 plus w, we must have alpha is 2 over 3 1 plus w. So we find that we have a solution for the scale factor for the flat universe. Here it is. There's some proportionality constant in front, but the main part is that A of t scales like time to the power of 2 or 3, 1 plus w. Since we generically expect omega, no, w to be bigger than -1. This means that the scale factor has a positive power here, so in the exponent, which means that the power of t is positive, and that means that the scale factor is always growing for a flat universe. Actually, we can sort of tighten the bound on w here, because for a flat universe, that implies that essentially the cosmological constant is 0. So we only have ordinary forms of matter. None of that have negative W. All of them have positive W. So we can actually sort of say that the power here actually has to be bigger than 2/3. Anyways, so the upshot is that for this particular case, we find that we have an expanding flat universe with the energy density being exactly equal to the critical energy density. And we can further sort of look at this in more detail by sort of trying to see how the scale factor depends on the precise matter content. So as I said, if we want to sort of have an actual solution, we need to say what the matter content is or what the equation of state is. So again, taking our example from early in the lecture, we can choose the equation of state to be that of dust, where W is equal to 0. So then we get that the scale factor scales as t to the 2/3. Or we could use a different equation of state that of a universe dominated by radiation, in which case you have an ideal gas equation of state, energy density is 3 times the pressure, or W is 1/3. So we get that the scale factor scales as t to the 1/2, which is slightly less than 2/3. So this universe dominated by dust is expanding more quickly than the radiation-dominated universe. Of course, in a realistic universe, we would expect there to be dust, radiation, and maybe some other forms of matter, with the effective W changing as a function of time, depending on which form of matter is dominating. Okay, if the universe sort of was very hot at some point, then more probably radiation is dominating. If it is cold, like our universe today, then most likely dust is dominating. We can go back and have a second look at the age of the universe now that we have a specific solution for the scale factor. Again, we fix the beginning of the universe at time is 0, and we define it by saying that the scale factor at this point has to be 0, which is well satisfied by our solutions for the scale factor. Then, of course, today's time is T0, and we can easily get our hands at today's Hubble constant, which is just A dot over A evaluated at T0. And that is just alpha over T0 for our explicit solution of the scale factor. Note that this is not an approximation, this is an exact consequence of the solution that we have. So obviously, this means that we can express today's times T0 in terms of alpha and the Hubble constant. And today's time is nothing else but the age of the universe. So we get that the age of the universe is alpha divided by h0. We can now use precise observational data for h0 and plug this in. So if we use something like 70 kilometers per second per megaparsec for the Hubble constant, this means that the age of the universe is 14 times alpha gigayears, so 10 to the 9 or billion years. So if we then say, well, what is alpha? We can plug in dust, where alpha is 2/3, and we find that the age of the universe has to be 9.3 billion years. Or we could put in radiation, where alpha is 1/2, where we find that the age of the universe is 7 gigayears. Now, both of those are problematic because they are both too short for the actual stars that we observe in our Milky Way, which are at least sort of 11 billion years old. So that problem is compounded by the fact that for a flat universe where we can't have a cosmological constant, the W has to be bigger than 0. So actually, dust is sort of the upper limit of the age of the universe if we restrict to equations of state that have W bigger than 0. And clearly, there's a tension between the age of the universe that we get for our explicit solution for the flat universe and the observed age of stars in our Milky Way. So the upshot of this is that a flat universe where kappa is 0 may be a theorist's universe, but it most likely is not our universe because the age of the universe doesn't match the observation for stars. So this clearly points to us having to sort of go back and find other solutions for the scale factor that allow different scenarios than the flat universe, which we'll do in the upcoming lectures.